I am going to introduce a linear algebra course in which all the problems will be solved with a single algorithm. Have you imagined a single and very simple algorithm able to solve all common problems of linear algebra? Would you like to know such algorithm? If this is so, this course will reveal to you one such algorithm. It will be explained in only 5 minutes, and using it you will be able to solve problems such as obtain the orthogonal subspace of another subspace, invert a matrix, calculate its determinant, know if a vector belongs to a linear subspace, obtain intersection of subspaces, solve system of linear equations, discuss the compatibility of these systems, etc. I invite you to travel with me in this interesting trip in which you will see linear algebra from the point of view of orthogonality, and you will discover new and very simple methods to solve algebra problems, avoiding some traditional, very painful ones. The idea is to explain you an orthogonalization algorithm that gives you the orthogonal subspace and the complementary space of a given subspace, and with that algorithm you will solve all these problems that you can see there. Invert matrices, calculate determinants, analyze the compatibility of system of equations, solve system of equations, obtain orthogonal subspaces, etc. The algorithm will consist in several steps in which we introduce vector by vector, and then we pivot and obtain tables similar to this one. The interesting thing is that if you introduce a vector, for example, consider in the matrix below, the first row is 1, 1, 0, 1. If you introduce the vector 1, 1, 0, 1, then you pivot and you obtain another table in iteration 2, then you will introduce the second row, which is 0, 1, 0, 1, there in iteration 2, and then you pivot, then you introduce the third, and you pivot, etc. And finally you will get a matrix that is at the end. The algorithm is designed to obtain the orthogonal subspace to a given subspace. For example, if I introduce the vector A1, 1, 1, 0, 1, and I pivot, in the second table, in iteration 2, I get the columns in blue are the generators and really the basis of the subspace which is orthogonal to A1, and the yellow one is the complementary generator. But there is a very interesting property. If I introduce A2 and pivot, I get a new matrix in iteration 3 that also satisfies the same property as iteration 2, because the blue vectors multiplied by the A1, if I multiply A1 scalarly with W2, B3 and B4, you get 0, and multiplied by the yellow, you get value 1. And if you introduce another vector A3 and you pivot, or A4 and you pivot, all the matrices maintain this property. This is a very interesting property. So, the last matrix has information about the orthogonal subspace and the complementary subspace. If I introduce the second vector, you obtain that in iteration 2, you obtain in iteration 3 the generators of the orthogonal subspace and the complementary space. And this information also is maintained in all the iterations. Finally, at the end, you have a table. I have reproduced here the table, and you can see the orthogonal subspace of the first to the first vector is in the first table on the top. But you can have also the orthogonal subspace to the second vector and the orthogonal to the third and to the fourth, just selecting the corresponding vectors. You have the matrices on the right, you have the row vectors, and on the left-hand side, in blue color, you have the generators in really the basis of the orthogonal subspace to each of these vectors. But even more, this last table contains information to obtain not only the orthogonal subspace to the subspace generated by one vector, but for any possible combination of vectors. So we can obtain the orthogonal subspaces to the first and the third, the first, second, and third, the first, the fourth, and second, any combination, just because these four vectors contain the information. And this is a very interesting result. For example, consider the matrix A that is there. Let's see how can we obtain the inverse of this matrix. We consider the first row, 1, 1, 0, 1. We put it in A1 in the first iteration, and then we pivot. We take next the second row, and we put it there, 0, 1, 0, 1, in the iteration 2, and we pivot. Then we include the third row, the 0, 0, minus 1, 1, and we pivot, and then the fourth one. And finally, after pivoting in iteration 5, we get a matrix in yellow color, which is the inverse of matrix A, as is written there. This happens only because we have pivoted in the order, the first with the first, the second with the second, the third with the third, and the fourth with the fourth. But if we pivot in different order, we just need to change the rows, as we will see later. Another interesting thing is that we can obtain the determinant just by multiplying the pivot values. You have the pivot values 1, 1, minus 1, and minus 1 in green color. If you multiply all these numbers, you get the determinant of the matrix. So with the same work, you can obtain the determinant, not only the inverse of a matrix. If you pivot in a different order, you need to make some changes so that the formula of the determinant is the determinant of the initial matrix. Normally we start the algorithm with the identity matrix. The determinant will be 1, but we can start with any non-singular matrix. Any matrix with a determinant different from 0 is valid to start. And then in the formula of the determinant, instead of value 1, we should use the inverse of the determinant of that matrix B. Then we multiply all the t values, which are the pivot values, and later we need to use the one factor that is minus 1 to raise to the p power. That means that depending on the number of columns that are switched, we need to change or not the sign of this determinant. So the formula is very simple. Another interesting thing of this algorithm is that we can update inverses if we change the rows. Assume, for example, that we have inverted a matrix 1000 by 1000, and after a very long work, we discover that one of the rows is wrong. What to do? We don't need to start from scratch. We just introduce the new row, we pivot one more, and then the final matrix is the updated matrix. And the same can be done with the determinant. The previous determinant is multiplied by the pivot, and then we get the new determinant. In the course, you will see this very easy. Another interesting property of this algorithm is that we can obtain the inverses of the matrices associated to the main diagonal of dimension 1, 2, 3, and 4. You have one matrix in yellow color, 1 by 1. You have one matrix in blue color, 2 by 2. You have one matrix in fuchsia color, 3 by 3. And finally, you have the whole matrix in green color. But look, the inverses of those matrices are all in these tables. The yellow one is in iteration 2, the 2 by 2 in blue color is in iteration 3, the 3 by 3 in fuchsia is there, and finally the green one is there. So this is an extra that you get when you pivot in order. Now let's move to the problem of determining the rank of a matrix. As you know, determining the rank of a matrix is complicated. It's very painful because you need to determine, calculate determinants 2 by 2, 3 by 3, 4 by 4, and they are very complicated. And then I am going to show you how to determine the rank of this matrix using the algorithm. Consider the matrix 4 by 4 that is there. What we do is we introduce row by row. You can do it with columns, but in this case we will do it with rows. We introduce the first row, 1, 1, 0, 1, and we pivot. Then we introduce the second row, 0, 1, 1, 1, and we pivot. We introduce the third 1, 1, 3, 2, 3, and then we discover that we cannot pivot because we get 0 dot products. And this means that this new vector is a linear combination of the previous one. And the algorithm not only informs us about this fact, but it gives which linear combination is the one that gives this vector. Because in blue, you have the dot products for 1 and 2. And this means that the first vector multiplied by 1 plus 2 times the second will give the third one. You can see the linear combination of the first 2 vectors equal to the third one in the lower part on the left. And then we discover that this is a linear combination. We introduce another vector, and then we also discover that the new vector is also a linear combination, and we discover which linear combination is 2 times the first vector plus 2 times the second. So because we have been able to pivot only twice, the rank of the matrix is 2. Look what a very nice way of determining the rank of a matrix compared with the traditional one. Of course, we can obtain the basis of a linear space using this technique because we are given a set of generators, we introduce one by one, and we discover which ones are linear combination of the previous. We remove them, and we obtain the basis very easily. The next problem we are going to analyze is if a vector v belongs to a linear space generated by vectors a1, a2, an. The first expression, v belongs to L of a1, a2, an, is a traditional way of seeing the membership of a vector to a linear space. However, we are going to write the second, the L linear space in a different form. We know that the orthogonal of the orthogonal of L is L itself. So we replace the L by the orthogonal of L. And then this is another way of seeing the same problem. But looking to that, we can also write that V should be perpendicular to the orthogonal of L. So this is a third way of seeing the same property. But now, this is telling us what to do to determine if a vector belongs to a linear subspace, because it's telling us the following. First, you need to determine the orthogonal subspace to the L space. And once you have determined that, you need to check that V is orthogonal to that subspace. That means multiplying scalarly V by all the generators, and if the products all are 0, then the vector will belong to the subspace, and otherwise it will not belong. So you can see that if we put the glasses, a new glasses that allows us to see the world from the orthogonality point of view, we discover one way of solving this problem. The following problem is the intersection of 2 linear subspaces. You can write it in the traditional way, S intersection of S2, or we can replace S2 by the orthogonal of the orthogonal, or perhaps S1 as the orthogonal of orthogonal. We have 3 different ways of expressing the same thing. But the second is telling you that the intersection is the orthogonal to the orthogonal of S2 in S1. I repeat, the S1 intersection of S2 is the orthogonal of the orthogonal of S2 in S1. And that is very easy to do because we have an algorithm that allows you to obtain the orthogonal subspace. So we can first obtain the orthogonal of S2 and then calculate the orthogonal of the resulting subspace in S1. And what to do? Instead of starting with the identity matrix in the algorithm, we start with a matrix that contains the generators of S1, and then this algorithm gives you the orthogonal, but in S1. So this is the way of solving the problem of intersection. Now, I am very happy to explain you how to solve a homogeneous system of linear equations. Normally, when you have a system of homogeneous system of linear equations, you have an expression like that: a11 x1 plus a12 x2 plus a1n xn equal to 0, and the same for the other equations. It is an homogeneous system of equations because all the independent terms are 0. Okay, but instead of looking to the system in that way, we are going to put our orthogonality classes and use orthogonality to write this system in a different form. Look, the first equation can be written as the dot product of the vector a11, a12, a1n times the vector of unknowns x1, x2, xn equal to 0, because the dot product is a11 x1 plus a12 x2 plus a1n xn, which is the first equation. And we can do the same with all the equations. But this form is telling us how to solve the problem. This form is telling us that the vector of unknowns, x1, x2, xn, is perpendicular to the vectors corresponding to the equations, to the coefficients of the equations. So, the solution of this homogeneous system of equations is the orthogonal subspace to the subspace generated by the coefficients of the rows. And this is, I think, a very interesting result. We know that the solution of a homogeneous system of equations is a linear subspace. First, we know that. And second, that the linear subspace is the orthogonal subspace to the subspace generated by the row coefficients of the rows. But even more, if we calculate the orthogonal subspace and we use the algorithm, we obtain a final table like that there. So you have one example of an homogeneous linear system of equations, and you have the final table that you obtain when you obtain the linear subspace to the vector generated by the rows. This is what you get. And this allows you to solve the system of equations. In this case, the solution of our system has only the zero solution. I have to say that any homogeneous system of equations has the zero solution, always has the zero solution, because if you put zeros in the x, you always get 0 no matter what coefficients you use. But because we have that table, we can consider any subsystem of equations, only the first, or the first and the second, the third and fourth and the first, the second, any combination. And all the solutions for those systems are contained in this table. We just need to choose the right columns to write the corresponding system, the subspaces. So, in this case, you have the solution of the whole system, which is unique, the zero vector. You have the solution of the last equation, x1 plus x2, x4 equal to 4. And then this linear subspace can be obtained just by removing the W4, which is the column we use for pivoting with that equation. If we have another two equations, as in the third case, we just need to remove the pivot columns that we use when you introduce the corresponding vectors. And the other two generate the solution of this vector. And in the last example, that you have three equations, you just need to remove in that final table three columns, the three columns that correspond to the pivots of the equation that are in the system, and the remaining one gives you the basis for the solution. So this way of solving the problem gives you the structure of the solution, which is a linear subspace, and gives you the solution not only of the system, but also of any subsystem of equation that you can consider. What happens if you have a complete linear system of equations? What happens if the right-hand side terms not all are zero? That we don't have zeros, and that is a problem. But we are going to do some interesting thing. We are going to invent a new unknown, because we have x1, x2, and xn. I am going to create a new unknown, which is xn plus 1. And I am going to multiply the b1, b2, bn by x1, x2, xn plus 1, xn plus 1, and xn plus 1, and move it to the other side as it is below. And then I get the zeros that I like. I have an homogeneous system. But because I have multiplied by xn plus 1, this system is not the same as the previous one, unless xn plus 1 is made equal to 1. If xn plus 1 is made equal to 1, then the system is the same. So what I do is, I solve first the homogeneous system of equation, excluding the last equation, and then from that solution, I take only those solutions that satisfy that xn plus 1 is equal to 1. So this interesting idea of thinking in a new unknown, an artificial unknown, allows us to solve the problem. And as before, we solve, with this method, we solve not only the linear system of equation that is given to us, we can also solve with the same information contained in the final table. After pivoting, we have information enough to solve any subsystem of equation. That is beautiful. You can see the structure, for example, in the second, or in the third case with two equations. You can see that the solution x1, x2, x3, x4 is a linear subspace of dimension 2, rho 1 times one vector plus rho 2 another vector. This is a linear subspace of dimension 2, plus a particular solution. This is the general solution, or the general structures, or the solutions of a complete system. It's always a particular solution plus a linear space. Another problem is the compatibility. Assume that you have a system of equations and you want to know the conditions under which b1, b2, bn give a system which is compatible. Then what we can do is to write the system in a third different way. Look that the system of equation above is equal to the equations below. The equation below says that the vector b1, b2, bn is a linear combination of column vectors of the coefficients of the system with coefficients x1, x2, xn. So the system is compatible if the vector b belongs to the linear subspace generated by the columns. So the columns of the complete system will give us information very important to see if the system is compatible or not. So the problem of compatibility reduces to a membership problem that we have been studied before. And this ends my summary about this course. You have seen that this is not a standard course, because though the problems dealt with are common, the way of solving them is new and based on the orthogonality concept. This permits you to see these problems from a new perspective. You already know about an algorithm that permits solving all these problems of linear algebra in a simple way, which is useful and interesting. You also know that the knowledge of the structure of the test of all feasible solutions, together with some mathematical information, permits obtaining immediately all feasible solutions of systems of linear equalities. If you think that this material could be relevant to your work and you want to incorporate this knowledge to your way of facing problems, you are invited to learn, enjoy, and discover a new world following this free course.